English. Okay, so hey everyone. Thanks again for coming. I'll be talking about automatic data discovery and augmentation, and basically the main point of the talk is to explain what it's all about. Okay, so I'll give some overview of the problem itself, and then I'll give an overview of a landscape of what's going on in dataset search and data augmentation steps. And I'll do that through going through some papers that I will use as a tool to discuss those topics. Omer Har, my CEO, is on the call, so I won't be able to share with you all our most kept secrets, but hopefully I'll be able to tell you some interesting things about it. Okay, so one sec about me. So my name is again Shai Yanovski. I'm the VP Data and Data Science in Explorium. About 12 years now in this constantly name-changing space of dealing with data and training machine learning models. Based in Tel Aviv, in Israel, and a father to a 3.5 years old daughter. Okay, I see that. I have some technical issue. I'm sorry, I will switch the network. Okay. So what we do in Explorium? So in Explorium, we develop a data science platform focused on augmenting and data enrichment and the feature discovery process. And actually, I'll be in a much better spot in explaining in more details what actually we're doing towards the end of the talk. I'll just say that we are based in Tel Aviv. R&D is based in Tel Aviv, and we have offices as well in the US. Very well funded, have a bunch of customers, big and small, and always looking for talented people to join us. Okay, so now let's get to the topic. So when we examine the overview of the AutoML landscape and the different components of the process, so it's usually start with getting the data, starting with the data, some labels sometimes, and putting all in this sophisticated machine that does all those different steps, extracting features, choosing model, tuning the model, things that Erez just talked about in details, and doing the evaluation and closing the loop. But this first step of getting the data is still mainly considered as something that is done by the human operator, the data scientist. And that actually is something that don't necessarily have to be this way. So let's see what can be done in this area. So we can break this box of getting the data or starting with the data into searching for the right data, getting it, acquiring it, cleaning, and integrating it all together into a nice, neat data set. We can break each one of those steps even further and go into more details about this step and about this process. I'll do that through a very simple example. So that's actually a real example of a competition that was done in New York using the taxi data, but not the Kaggle taxi. The Department of Road Safety did a competition asking people to predict the fatalities of road accidents in New York. And if we started with a very basic data set, so we have some timestamp, we have a location, and we have a number of trips on the location in the timestamp. So we do some research, maybe run some our favorite algorithms, so maybe a bunch of them in some AutoML model, and we end up with, say, random forest, and get some eventual results. So what we can do next, how we can continue. So Generally speaking, we have two things to play with. We can play with the model. We can try to tweak and try different configurations in the model, but we also can try to do some things with the data. And as you can probably guess, in this talk, I'll focus on the data part. So the first, maybe the obvious thing to do is to try to get more data. And if we ended up finding some data of the same form, of the same type, we can just add those records, and probably we will have improved performance. But that's not the only thing that we can do. And if we found some relevant data that can augment our model, that additional features that we can take into account, say weather data, because we have some assumption that it might be relevant to traffic accidents. So we can add those things, we can join those records, add additional features, and from this type of addition, sometimes the gain is much more dramatic. So to sum those things together, we can say that there are two types of augmentation: get more features, join datasets, and get more records, do a union between the datasets. So that can lead us to suggest some formulation for the problem. So given an input dataset D, efficiently and effectively discover a set of datasets that can be used to augment D and rank them with respect to their ability to improve performance on some task T. Any questions so far? I actually encourage you to ask in the middle. Okay, so ask in the end. Okay, so as you can imagine, if we open that direction, there are a lot of different datasets that we can get. We can get the road condition, we can get if the road was covered with ice, if there are bicycle lanes nearby, if people are tweeting around and because there is some event and there is more dense population in this area, etc., etc. But how we get that? I mean, okay, that's nice in theory, but what would the system that actually help us to do that manual work would look like? And what are the challenges that we need to solve? So first of all, it's a lot of work. As people that saw some early version of this presentation commented, it's not only a theoretical work, but there's a lot of engineering work, not only getting this data set, but the pipeline that will provide us this data in predict time. So it's nice to get some dump of tweets, but we actually need a pipeline to do that in prediction. And it's all true, but let's assume that it's something that we actually can do something with, and let's continue. Okay, so let's get to finding the data. So I used, I took a fragment of a very nice survey of this area of data search, and I'll talk a little bit about the different areas of what can be done there. So first of all, we can distinguish between the type of search when we search for data sets. And I think the most common and obvious to all of us is databases. So we all you all work in companies that have databases, and if you have access to those databases, there are pretty good tooling in querying those data sets and manipulating them and joining them and eventually getting a set of records that you can use as a potential to your model. But obviously that's not all our world is mapped to databases, unfortunately. So the next approach is the information retrieval approach. So that's seems more like the familiar thing from Google, and even they actually about 2 years ago released the dataset search, which use similar paradigms to the Google search that we used to search for datasets, but in a very open-ended manner. So we can type a keyword about whatever we are interested in and get a bunch of results, not necessarily structured the way we want. Not obviously building this type of systems is completely different than searching in a database, but those systems are getting more and more common. Entity-centric search, so those are more specialized systems that are built around a certain entity. So IMDb is a very common example. If you want to look for a movie, we can have a very structured way to look for movies that we are interested in, and to extract a much more standardized, much more nicely behaving rule set, data set coming from that source. And the last bullet is tabular search. It was mentioned in this survey. I must say that I personally got to work on some variation of trying to extract data from just tables in the web about 12 years ago. And I think this unfortunately stay relatively theoretic and academic work. So what actually can be done there is to build web spiders, web scraping systems that can get this data, but all the burden of parsing it and cleaning it and turning it into something that we can join to our system is still something that there is no general purpose working solution that solves that once and for all. So it's a pretty customized effort. Okay, so now it's not that every system have to choose only one approach. If we take a Google dataset search, for example, so they provide a combination. So we can search by entities, we can search by keywords, and other systems in this space also provide sometimes more than one way to search for the data. A brief overview of the types of sources. So there are some open data government sources, data portals that allow providing those various facilities to look for different data sets. There is an enterprise equivalent for that in some organizations. Scientific community is also relatively very participant in that. And what we see lately is more and more commercial sources, data marketplaces that also facilitate searching for data sets, but via commercial means. There is other very promising, but again, relatively still academic area of linked data. So the premise is very nice. The premise is using the same set of schemas and ontologies and describing the data in the same way. So the various databases will be connected. So this space is growing and growing. There are more and more databases that are described in this manner. But again, to tell you from the practitioner side, it's not an answer to all our needs yet, but it's getting a boost from mainly from Google and Facebook recently, because it's very convenient for them to use that paradigm to structure the data, to use that for their own products. And that's an example of AWS Data Exchange. So that's an example of a commercial proprietary data. So what would the system look like? And that's an example for Octus Data Mart. It's a project by NYU. So there is a layer of data discovery. So whether it can be scraping of web crawlers to get to less structured data, to some connections drivers that can actually connect to some more structured data sources. Then there is a profiling layer, which extracts different features about the data itself, but also different features about those data sets and store them. And then we have this ability to match and to rank using those data sets against any particular case. So you can start imagining that how this component can work. Once we get a data set, we can get to all this catalog of the possible data sets and look for candidates for us to get into our AutoML process. An additional very important remark, Noam, that's thanks to you, is that we obviously need to think about the predict time. So for some examples, it may be less trivial, maybe so, I mean, more trivial. if we, I don't know, looking for images of cats, so maybe it's okay to get a bunch of them in the training set from somewhere, and then we have a cat classifier. But if we need to use data that we not necessarily have access to in the training time, so making sure that this system can provide us an ongoing access to the data is an important piece. Okay, so now we found a lot of candidates. What's next? And the next is entity augmentation, or dataset augmentation. And here, I'm not talking about augmentation in the image recognition sense and manipulating the images and twisting them, but actually this task of joining the datasets together into one big tabular dataset. And actually, even here, there is a nice meta here that disambiguation, so the same term means different things, is something that is a core challenge here in this piece, because as you can imagine, different datasets coming from different sources can contain a key that are the same key, but talking about two different places or two different persons, or two different, I don't know, companies, and vice versa. The same entity can be described by different keys, whether it's by a mistake or because the convention is different. So again, this paper, the ARDA, they propose a system that does the whole loop, and I have a slide with all the references in the end of the talk, so you can go and read full details if I miss anything that is interesting to you. Okay, so the basic components are the connection to the ability to get potential datasets, a formatting piece, a component that does the join plan. I'll touch the join part in details. Actually doing the join and calculating in which order we'd like to do those joins. Then doing a full AutoML cycle of actually extracting features, imputing the missing data, formatting, etc., training the model, evaluating, and then doing the loop again. Okay, so the first thing is that if we got several data sets and we want to use them, we need to find a way to join them. So first of all, the thing that we would do is make sure that in the candidate, we bring all the relevant records, but not the other way around. So it might be trivial, but that's the way we start. We want to bring all the data from our core data set, but only the relevant things from the candidate. And that's our first opportunity to kind of get the sense if the candidate is worth or not. So say if this union is very small, so we don't have much records augmenting the core data set that we want to train, it's probably not a very interesting candidate. The cardinality of this join might differ. So for the same, say, let's stick with the example of the road accidents. So for the same location, we might have a various number of records in our candidate table. So let's say if you're bringing some, I don't know, tweets from Twitter. So for some location, we might have only one tweet. Some location, we will have thousands of tweets. If we do something very naive here and just join them, we will introduce a very big skew into our dataset. So the solution that was proposed, and it's actually something that we are doing as well, is to do aggregations. So it can be anything from a very simple aggregation of just taking the mean or sampling if it's a categorical data, but it also can be something very proprietary that is relevant to this specific type of entity. And in a more general sense, it's actually something that can be treated as an additional hyperparameter in the general sense of how we do this join. We can add it as a hyperparameter to our AutoML framework and to experiment with different strategies. Joining on times have its own challenges, so I won't have time to get into all the details, but just to give you some taste. The resolution, the precision can be different, so we'll need to treat that in some way to compensate that in some places the precision is in hours, while the other in days, and actually it can introduce then again a skew of one to many, so we need some strategy to aggregate those things. Hard joins versus soft joins. So when everything is neat and clean, so we can just do join field A in table A versus field B in table B, should match exactly. But if the data sets coming from outside are not created in the same process, there are many, many reasons that hard joins won't just work. So manipulating the inputs is a very active topic, or record linkage or entity matching. All those terms are in this area of how to join datasets that are not joined precisely by their hard key. So as I mentioned, the reasons for that are anything from missing data to typos to different conventions, etc., etc. So there are many different methods. In this paper, they evaluated a few and proposed their own. I give you here a list of very common methods that you probably are aware, at least with some of them, but just keep in mind that the additional challenge here is to do that in big scale, because if we have thousands of data sets as candidates, so we need to think about how to do that in a scalable enough way to try to do that actually with all the potential data sets. Geospatial joins is an additional interesting and challenging topic. So we talked about in our original problem that we have some location ID, and say we would like to know if there is a school nearby. So what's actually nearby? Is it on the same coordinates, or is within some certain distance? Or we would like to understand if it's actually relative to some area. So we have a school in this neighborhood. All those questions, all those ways to ask if this location space is related to our core dataset will define a geospatial joint calculation. And again, doing that in scale, it's an interesting topic that is still active. So there are some interesting things being released every time. And like of course, we have aggregation of both concepts. So we can encounter situations when we will have to do both. Aggregate by geography and in time. So say how many people are passing in a certain point. So it's not on this specific second, but we would like to see how it behaves over time, maybe to understand in every specific location, how many people are passing there in the business hours, at night hours, and to come up with some both on time axis and space axis aggregated features that can be joined into our data set. Okay, so now ranking. So what we join first, what we join later. So it's in this paper they did a pretty naive approach, looking at the cardinality, so the size of the join. I would say that it's very well, from our experience in Explorium, it's very well related to what Noam will talk in the next talk, and that's trying to use some metadata and trying to build some kind of accumulated intuition or meta learning, if you will, that will provide using the context of the data set to the problem and rank it by that way. Now what we do when we joined it all together. So in this paper, they proposed using some dimensionality reduction schemes. So basically things like PCA. But an additional piece that is very standard at this point is the feature generation. So we all know that as practitioners that when you have your initial original dataset, the data is not necessarily goes straight into the model, and there is a piece of extracting features. So there are some works on how to do that automatically as well. So say just a very simple example, taking a date and extracting if it's a weekday. This step can be mapped into every date in our dataset and can be suggested as a candidate feature to the model. When we're talking about more complex joins, obviously the space of different aggregations is much bigger. And then we get into the feature selection phase. So in the paper that I mentioned, they did some evaluation and suggested some methods, but which wasn't leading well above the other methods. And actually from our experience, that's a very interesting and challenging topic. So how to do feature selection in such a big scale. And it's one of those areas that there is no free lunch. There is no one solution that just leads. Quoting from a review that was just released this year, they conclude there is no group of filter methods that's always outperform other methods, but they found that there are similarities. So some methods are very correlated to each other, and that's not surprising. So methods that very heavily based on, say, information theoretic approaches tend to get to similar conclusions in the feature they suggest. There's also a trade-off between running the feature, performing the feature selection and the runtime of this step. So there is in this paper some analysis of that. It's a bit misleading because the y-axis in a logarithmic scale, so the differences in performance are actually not that dramatic in their paper. Okay, so that was kind of the overview of the challenges along the way, and that brings me to, I have 2 minutes to come back and say what we actually do in Explorium, and we're actually trying to tackle that. So coming from an understanding that currently the data scientists and companies are mainly have access to data coming from their own organization, and maybe some data sets coming from outside, are missing this option of using this wealth of data in their models. And it's very clear why, because the challenges are clear and not all of them are solved and accessible, but that's what we are trying to do easier for the data scientist teams. Actually take all this wealth of data and build those facilities that can bring that into your models more easily. So basically, we have all those layers in our platform, a catalog of external data sources, a layer of automated feature generation, and the feature selection, and then we use an AutoML step as a proxy to understand which features are contributing to the model, and eventually enabling to create a model that can be deployed into production. As I mentioned, it's all wrapped in a very nice user-friendly platform, and those of you who will be interested can obviously come to our site or talk directly with us. But that's just to complete the whole cycle. Those are the references that I promised, and thank you very much for your attention.
Hey, thank you, Shai. Okay, so I'll take it from here.